Yes. Okay.
Okay, nice. So, hello everyone. I'm Yanyan. Thank you for inviting me to give a talk today, and apologize that I cannot go to the symposium at Warsaw in person due to some personal reason. And it's really a big pity because I already saw some of my friends in this room, and hello again to my friends. And thank you the organizers for allowing me to give my talk remotely. So today I'm going to talk about searches for gravitational waves emitted from collapsed supernova. I would like to give a brief overview about the past and present searches, and also the possible future searches, assuming the detectors will be able to run in future. Okay. So today I don't need to start my talk by introducing what is supernova, but I still put this slide here. I would like to share with you these beautiful images and also remind us that we are working on one of the most beautiful phenomena in the universe. So supernova is a dramatic explosions, and as we know, 99% of energies are emitted by neutrinos and 1% are emitted by gravitational waves. So the intensity of gravitational waves and the detector sensitivity, due to that, we expect to detect gravitational waves from galactic supernova. But due to the previous search, we can see there are only 1 or 2 per century for the galactic supernova exploded. And the last known supernova occurred in Milky Way was around 300 years ago, which is the famous supernova 1987A. When we are waiting for our next galactic supernova, we can still do researches for the closest supernova we can get. So also there are around 4 supernova exploded per year up to 20 megaparsec. So that's our target. So to search for gravitational waves, of course, we need a gravitational wave detector. A lot of people here already know a lot about the LEGO stuff, but let me give a brief recap about the observing runs. So the first observing run, which is O1, starting from almost 10 years ago. So the first and second observing run start from 2015 to 2017. The third observing run, which is O3, started from 2019 to 2020. And now the fourth observing run, which is O4, is ongoing. It is started from 2023 and will be ended until this November. So now the LEGO Hanford, LEGO Livingston, and Virgo is in operations. So we can do research with the data with them. So in general, so to search for gravitational waves, there are 2 kinds. One is modeled search and unmodeled searches for different sources. So there are 4 kinds of sources we usually classified. First is a compact binary coalescences. We call it CBC for short. And then burst transient, continuous wave, and stochastic background. For modeled searches, usually we use it to detect the CBC sources because the waveforms from the CBC sources are well studied. We can even build a template bank to perform the matched filter searches, one techniques from the signal processing. Related to the search time, we can do the low latency and offline searches. So far, there are around 300 gravitational waves from CBC sources have been detected. And another kind of search is unmodeled search. It's also classified to all-sky searches and targeted searches. All-sky, from the name, you can see it searches our time and our sky. It can be performed in low latency and low latency scale and also offline searches. For a targeted search, this is what we usually use to do supernova searches. So which means we use external triggers from the observatory. In this case, we will know the sky location of this target and also the search period. We usually do it offline. So let me talk more about searches for supernova. So in our group, Supernova group, so we perform an optical triggered search. So which means when a supernova explodes, so our team, we can collect the supernova information from different observatories. In this case, we can find the discovery time, sky location, and electrical data. Then we determine the onset window, which is the time window that the gravitational waves may be emitted. So usually this time is depending on the progenitor star's material, the masses, and other parameters. So after we can constrain the search time and the sky location, we can run the search pipeline. First, we do the closed box searches. It means we will only use the time shifted data. So we shifted the data manually so that all the triggers or all the events we found in this search are caused by noise. In this way, we can estimate how noisy our background is. And also, we can also choose the search parameter to avoid biasing ourselves. After the parameters is well tuned, then we can open the box, which means we can really run the search pipeline on the data within the on-source window. So then we can see if we can find any significant event. So in this step, we can see if we are able to identify any gravitational waves from supernova. So the last step is we also do some analysis, put some constraint analysis detection sensitivities. Basically, this is the workflow we usually do in supernova group. So the first targeted search on Cockclip supernova was made in 2016. So at that time, the data from the first generation of initial LIGO and GEO and Virgo data were used. So you can see and collect data from 2005 to 2011. So the four supernova was targeted within 15 megaparsec. From the left panel, you can see the four supernova and the box length indicates the onset window, and the different color inside the box indicates the different detector status, like this. So with this four supernova, no gravitational waves were identified. But then also do some simulation to estimate the detection efficiency as a function of distance for different supernova waveforms. So then found the distance out to which then can find the signal detectable. It's less than 1 kiloparsec for simulated waveforms. For the extremely models, it's up to 1 megaparsec. Then also put a constraint on the energies. And yes, it's around 0.1 solar energy and 10 solar energy above 1 kilohertz. This is the first search. So continue, then we came to the, we have the 0102 searches. So the similar searches were also performed. So there were 5 supernova candidates were targeted. So up to 20 megaparsec due to the detector was upgraded. No gravitational waves were identified either. So similar, the distance at 50% detection efficiency is improved compared to the first search. So it's 5 kiloparsec for neutrino-driven explosions, 54 kiloparsec for the magneto-rotationally driven explosions, and the extremely emissions is 28 megaparsec. And the constraint on energy is also better than the first one. And keep our search for the O3. That's also where I started contributing on the searches. So there are 8 supernovae up to 30 megaparsec. So no gravitational waves were identified. The closest supernova is 50.7 megaparsec. But if you notice in 0102, the closest supernova is one supernova exploded in 2017. The distance was the 6.7 megaparsec. That one is one of the closest supernova in the last 10 years. So yeah, similar analysis was performed. The detection distance is improved, And the constraint is also improved. But this time we also put a constraint on luminosity and protein neutron star ellipticities. And yeah, now I would like to talk more details about the recent search for gravitational waves from one significant supernova, which is supernova 2023 IXF. So because O4 is still ongoing and we are still working for researches in O4, but research this work was published recently, just a few months ago. So this is our most recent research result. So this supernova is located in the galaxy M1001. The distance is also 6.7 megaparsec, similar distance as the one exploded in 2017. So that's why it makes this supernova more interesting. The discovery time is in May 19th, 2023, just 1 week before O4 started. So at that time, the detector was in the 15th engineering run. So we have LIGO and LIGO was in operation, so we can have some data to do the searches. So following our workflow, that I mentioned before. So first thing, we need to estimate the on-source window, which is a time window that we perform research. The on-source window is estimated from May 13th to May 18th, 5 days. So it's related to the collapse, the time between collapse and shock breakout. And you can also see the light curve from this plot. So y-axis is the magnitude, x-axis is the on-source window, T2 is the end of the on-source window. So you can see we have collected light curves from different observatories so that we can estimate the shock breakout time and also the time delay so that we can constrain the on-source window. So inside this plot, there is a small plot inserted, which is showing the duty factor for LIGO Livingston and LIGO Hanford. It shows the detector status within the on-source window. So the coincident data between Hanford and Livingston is around 0.8 days. But however, sometimes the data quality is really poor, so we removed these times with a lot of glitches. So after cleaning the data, there are around 0.68 days of data that we can use to do research, roughly around 15% data within the on-source window. So the search pipeline, yes, I think probably a lot of people already know very well about it. Just a brief recap. So the search pipeline in research is a coherent wave burst. It's well developed and widely used search pipeline in LIGO since 2003. So it combines our data from different detectors and compute the constraint maximum likelihood. So the version we used in research is CWBXP, which combines the cross-power statistics. This is the search pipeline we use. So with this search pipeline, we performed the closed box and then open box. So here I will show you the open box result directly. So the loudest event we found from the box has a false alarm rate of 2.11 per day. So the loudest event means the event or the trigger with the lowest false alarm rate. And the false alarm rate means how frequently that a noise is identified as a signal. So 2.11 per day means the frequency that the noise was identified as a signal like this occurred 2 times a day. It gives a false alarm probability of 55%, which means that there are 55% of probability that the noise would produce a trigger like this. We also checked the false alarm probability curve as a function of ranking statistic row for background and for the loudest event. So from this plot, you can see the loudest event align with the background. And when we open a box, we also see the spectrogram. So this is spectrogram for latest event for Livingston and Hanford. So from spectrogram, it's very difficult to identify any gravitational wave signals. So combine all of them. So we think that this trigger is most likely due to the noise. So no gravitational waves was identified for this supernova. But as we mentioned, we can do some more analysis. For example, the most common analysis is the detection distance, which was performed in previous searches. So what we do is we collect the signal models and add these waveforms, these models, to detect coincident data within the answers window for a scale location of the supernova. Then we detect we compute the detection efficiency, which means how many injections can be recovered, the percentage of the event can be recovered. So in this search, we collected 14 simulated supernova waveforms from neutrino-driven mechanism waveforms. Here shows an example of the waveform we use. We try to cover more parameter space. You can see the progenitor mass from 3.5 to 14 solar mass. And also the rapid rotating waveforms. We have 5 models and also the PNS phase transition model. We also consider the extreme emission model, which is long-lasting bar mode. So here we use 40 Gaussian waveform to represent this model. So the tau varies from 1 to 1000 millisecond. Frequency varies from 55 to 2000 hertz. So this is waveforms we use. Then we add these waveforms in the data. We get our distance at 90% of detection efficiency, which means at which we can recover 90% of the added signals. So from this result, we can see for this analysis, we use false alarm rate of 1 over 10 years, corresponding to a FAP of 1.9 times 10 to negative 4. So for the non-rotating models, the distance can be reached up to 6.9 kiloparsec. For the more extremely models, the distance reached to 29.9 kiloparsec. So, which means none of these models from the numerical simulations can be detected at the distance of the supernova. For the long-lasting bar mode, which is extremely emission models, we also show a plot, which is detection efficiency as a function of distance. So we can see when the sensitivity increased when the signal's peak frequency and duration increased from this plot. In this plot, we assume the ellipticity, which is deformation of the star, is 0.1. And we also try to vary the ellipticity. Then we see for the low frequencies, if we want to detect, then the source will need to be highly deformed, which means epsilon is much larger than 1. So this is our analysis about detection distance. So we also put the constraint on the energy. So the energy for the rapid rotating supernova, which is the long-lasting bar mode we just showed, can be computed from the distance of the target, the central frequency, and the gravitational wave stream. So this plot shows the energy for all the 40 waveforms. The shaded area, this region, shows all the energies we get from 40 waveforms. Y-axis is energy, x-axis is frequency. So different markers show the different duration for waveform. So the red line shows the most stringent constraint we have, and the black line shows the constraint from O3 result, so that we can compare our searches with the previous result. So we found that at 82 Hertz, the most stringent energy constraint are around 1 times 10 to negative 4 solar energy. And compared to O3, this constraint is around 49 times better than O3. So it's a big improvement. Similarly, we can also put a constraint in luminosity. So luminosity is the ratio between the emitted energy and the duration. So we have a similar plot, but for the luminosity, so the constraint is around 2.6 times 10 to negative 4 for a signal at 82 Hertz, and it's 36 times more stringent than the one from O3. And another constraint we put is ellipticity. So we can compute the ellipticity based on this equation. And here shows how the ellipticity varies for different waveforms. So the most stringent ellipticity we get is 1.008 at 2000 Hertz. And overall frequency range is around 6.8 times better than the O3. So these are the three constraints we performed for this supernova. So here are, this is the recent search result for supernova 2023 IXF. Now O4 is ongoing, so let me remind you. So in O4, we have three phases, O4A, O4B, and O4C. So O4A, in O4A, because we want to be able to join at that time, so we only have the data from Livingston and Hanford. So the coincident data, which is the duty factor for two detector, is 53.4, not bad. For O4B, so we were joined, so we have the triple interferometer for 31.1% and the double interferometer for 36.8. For O4C, it's still running, so you can see how the detect status. Of course, all this information is public. You can find it online. So during O4A, O4B, and O4C, so there are around 14 collapse supernova exploded within 30 megaparsec and have enough electrical data. So therefore, from O4A, 8 from O4B, and 1 from the engineering run, which is between O4A and O4B. This supernova from engineering run, Supernova 2024 GGI, is also interesting because it also has a distance of 6.7 megaparsec. It's the third closest supernova exploded in the last 10 years. So makes things more interesting. So the discovery time is in April 11, 2024. You can see it from here. So these are supernova exploded during O4A and O4B. I think it's time to close this topic. So a brief summary, no gravitational waves from core collapse supernova was identified so far. And the detection range can reach up to the galactic center for some supernovas, and we expect it can reach further in the future rounds when the detector sensitivity is improved. And now we can set constraints on the energy, luminosity, and ellipticity. So to be continued, since this is the symposium and a lot of supernova experts here. So I'm also thinking we can work together to improve the current searches with ground-based detectors, and we can also have new ideas about the searching method, and also we also would like to provide information for supernova modelers from the detection side, since we get a lot of help from that. And again, all the work I presented today is not my own work, it's our team's work. So thank everyone in our team, for their big contribution for the supernova searches. Okay, thank you.
Thank you, Yanyan.
Yeah.
Any question in the room for Yanyan? Yes.
Oops. Oops.
Hi, Yanyan. I'm Christine
Hello.
here. Thank you very much for the nice talk. So I just have a quick question about like the energy versus like frequency plot, where you showed like this a couple of data points, and I believe this is like made using the long-lasting bar mode. But
Yes.
looking at I was just like pulling up the paper and having a look. You have like long-lasting bar modes of like 82 hertz, 200
Yeah.
hertz, and 2000 hertz. So can I know where the like in-between data points come from?
In between.
Yeah, so like there are
So
like data points that
like
are
here,
not.
right? Like here,
Yeah.
right? Okay.
Yeah.
So actually, so for long-lasting bar mode, we use 40 waveforms. So these 40 waveforms then have different frequencies and different durations. So duration, we have 4 durations. And we vary the frequency. We have 10 values for frequency from 55 to 2000. So 4 times 10, so we have 40. So which means the frequency in between actually is from 82. I think the next value should be 82, 112 to 182 until 2000. Yes. Yeah.
There's another question, Thomas. It's coming. Yeah, microphone is coming. Yes.
I may have been partially addressed. I was also wondering about these bar mode, long-lasting bar mode models. What's these models? I haven't heard about them. Which models does that refer to?
Okay, so this model, we use this model since 03. Actually, this is a model developed by Pablo. So I think probably it has another name in the 03 searches. I'm not sure if I show it here. So we call it no, no, 03. No, I don't put it here. So you use it for the short name we use it for LB. But I'm pretty sure this work Pablo has some publication related to this work. I don't remember.
He's sitting in front of me. I hand the microphone to him. Maybe he can explain what the model is.
Pablo is here. That's great. So I don't need to remember the possible publication where it will from.
So no, the model is very simple. It's just a deformed object with some quadrupolar deformation that you can parameterize with ellipticity, and it's just rotating at a frequency, and it has a rotation with just a Gaussian enveloped. So it's just that. It's minimally assumption about what is going on.
So it's a handmade model.
Yes.
Thanks a lot, both to both of you.
Thank you, Pablo.
Okay, there is another question in the room.
So thank you for the nice talk. Just a very quick question. So at the beginning, I think you mentioned that for this targeted search, you can use the constraint sky location, but later in this talk, it's more about using an on-source window. I think that's more about a time constraint. I just wonder if there's any sky location information used in the actual search.
Yes, because when we do a closed box, when we do an open box searches, we of course we search only for data within on-source window. In this case, we don't consider the sky location. But in the following analysis, for example, when we estimate the detection distance, in this case, we need to inject the waveforms in the data within the on-source window of course, and also for the sky location of this supernova. So that's why we perform the targeted search, because our search, when we inject signal, we also inject the signal in the sky location of that supernova.
Okay, so maybe one quick follow-up. So for the open box search, is there a particular reason that the sky location is not involved, or if it does help, what would you expect? How would you expect it to help in any way?
Yeah, interesting question. So, because usually when we do the open box searches, we just look at we just focus on data. We look at what can we find in this data, because we expect if we can detect gravitation from this supernova, we should be able to see it in the data itself. But I'm also thinking if it's possible to do the searches. I mean, open box, not only look at the specific time range, but also look at the specific sky location. But at this moment, we haven't considered it in open box results. But we might try to add the sky location later. Yes?
Hi, it's Jade.
Yes.
So I just wanted to say I went to Amaldi last week and someone actually gave a presentation about this where you do fix the sky position. It helps, but only a really teeny bit. That's what was presented last week.
Okay. Nice. Thank you, Jade. It's good to know.
Yeah, just to add a little comment about it. you can use the sky location, but the question is that where is the reconstructed location of the gravitational wave? So if it gets reconstructed in the wrong location, it doesn't help you to know the right location.
Last question, Yanyan. For the 2024 GGI supernova, what about the estimated on-source window duration and the duty cycle?
Actually, we estimate the duty cycle and the coincident data. Actually, it's slightly better than XF.
No, but for I mean,
Mhm.
oh, so this is similar, is what you mean?
It's actually we have more coincident
You're not
data.
supposed to say it.
Yes.
It was just the on-source window duration. Okay, estimate. Okay, sorry.
Yes.
Sorry. Well, I know, but we, but we listed it. It's in the list of the one we
Sorry,
have.
I'm not supposed to answer, but once you ask, I just cannot stop to answer.
Oh, that happened.
That doesn't mean that we are going to analyze all.
Okay, sorry. All right, this is the right answer. Sorry. Maybe not, but we. Well, I know. But I think in terms of no, it's not. Well, okay, I don't know. Oh, okay, fine. Okay, sorry.
It's okay. We can discuss it in the next supernova call.
All right. Okay, does not really matter. Okay, thanks a lot, Yanyan.
Thank you.
I think that's the
Thank
end.
you, everyone. Thank you.
Yeah.